Hello, I'm Tomasz Tarczyński. I work at Gigaset, and I would like to tell you today a story about how we evolve our backend platform for our IoT system. So first things first, as we'll be talking today about smart home systems. So I would like to ask you in the audience, how many of you use any kind of those smart home devices, being lightning bulbs, thermostats, vacuum cleaners, any of those, by a show of hands? Okay. And how many of you have thought about how those things work behind the scenes? So what's required for those to operate? Thanks. And one more question, as I presume there might be some hackers among you. So how many of you have tried to build anything like that yourself, to have some automation? Thank you. So I will try to tell you today how we are building such a system at Gigaset. Starting with the basics, so you probably already know those stuff, but just to recap, what makes an IoT system. We've got three main parts of it, and first there are devices in the IoT. So we've got different kinds of sensors. They might be door, window, motion sensor, or smoke, water sensor. There are different actors like a smart plug or a siren. And we also connect another devices like smart cameras or voice over IP phones to the same system. On the other end of the system, we've got our users, and they need to interact with it to see what's going on at home, so they got front ends. There are smartphone applications, and there's also another kind of front ends that you control with your voice, so things like Google Home Assistant or Amazon Alexa. And for those two parts to work together, we need something in between, and it is our backend that runs in the cloud, so all the servers for this both parts on both sides to communicate. What's required for such an IoT backend? As we've got all those devices, they need to send signal to the servers in cloud, so we need API for devices. Our users need to see what's going on, so we need another API for the front-end applications. Then our users require to see results, to be notified immediately about anything happening, so we need very fast processing of all the events. And also, to enable our users to see history of what's happened, we need storage for events. And we also have non-functional requirements, and there are two of those most important. So we need the system to be really reliable. So basically, all the features that we have there, they are not worth much if the system happens to be not available for some time. We should keep it always up, always respond correctly. So if you go for a history of events at home, if it's incomplete, it's a bad experience for our users. Also, if you need to wait long for results, like you request some information and wait for a second or two, it also gives bad experience for users. And another requirement here is velocity. So basically, to compete in this smart home market, we need to provide new features really frequently, do it fast. It means providing new sensors, new devices to our users, and new functionality in front-end applications. To do this, our backend platform also needs to evolve rapidly. While doing this, we need also to ensure that we don't break stuff that's already there. And what's more, if any kinds of bugs happens, then we need to be able to fix them rapidly, so to restore functionality for users. So how we are building this system? We've started some years ago with the first generation, how we called it, and basically we've built a monolith. So there was a single backend application with all the functionality within it, and we deployed it in infrastructure as a service from a cloud provider. Just to give you a very simple view of architecture, it looks quite simple, like the devices and users sending requests to reverse proxy server, which then forwards them to the single monolithic application, and there's data store at the bottom. We also needed to make it resilient to failures of single components, so we added multiple instances for high availability and load balancers. So very simplified view of it would be like this. And just few words about people building this system. So there were two main groups. There were developers, and for them the main goal is to deliver new features as fast as possible. So to put new versions of this app to production. And there are operations. So another group focused mainly on reliability. So goal of this group is to make it always available, always work good. And as you can imagine, those two goals of those groups are in conflict. So back then, our cooperation wasn't really smooth. It was about a lot of issues when we tried to work together to develop this thing. And we see some different limitations, different issues with our one big monolith. So first of them was that we had really big releases. It was a very time-consuming exercise to release a new version. For example, we needed to make very detailed tests in test lab, which took us something like 1 week to test all the features in backend. Also, deploying this thing to production, it was also very difficult. So it took us something like 2 days of manual work done by operations, and it was also error prone. So we've seen quite many failures. It's because, except those this architecture of the system, it seems very simple, but a lot of complexity was hidden inside this single app. It was all different features interacting with each other. So we had quite many failures, both in operation and during deployments of new versions. And as an effect of this, our releases were really not frequent. We were able to release a new version once per month, and doesn't matter how hard we tried, we couldn't do any better. Another issue was the coupling of work. So basically, what developers did, there were something like 20 developers working on different features, but then if they needed to deploy something new, they need very exact planning and to schedule things with other teams. So they needed to check with front-end developers, with operations, with test lab. It all needed to be planned carefully. And also, their work was tightly coupled within the team. So basically, if one of them was working on one feature and another on something different, to release this thing to our users, we needed all the work to be completed, tested, and bug-free. So if any bug happened in any feature, it stopped the whole show from going out. And everyone else needed to wait for this to be fixed. So, because of those issues, we decided that we need to change. And we thought it would be good to go for microservices. And just to tell you a few words why we had this idea. First off, the reasons was to decouple development of the different features. So basically, if we split our one big application into many small specialized pieces, then we should be able to deploy each of them independently. So when developer finishes the work on one feature, they should be able to just deploy it, and don't need to wait anymore for different team members. Frequency of deployments should go up. And it's because, again, if this work is done independently, each of the components, of small applications, we should be able to deploy them frequently, like iterate on daily basis, not once per month. The risk of deployment should go significantly down, and it's also because of this frequency of what cycle do we work in. So basically with the old approach, we were releasing a month of work to production. With small applications, it is effect of something like maybe 2 days of work. So then if any bug should happen, we are also able to fix it easily, because for a developer it's much easier to remember what he worked on yesterday. And as a result of all those, it should also allow us to move much faster. So have a faster pace of moving from having an idea of what we want to implement to putting it to our customers. So just this clock time from idea to customer using the feature should go down. How we do this? So we split our one big monolith into many single-purpose applications. Currently, we've got around 70 of those. And each of those applications is now developed by only 1 or 2 developers. They can focus on one thing. And actually, the size of this microservice is such that it's easily understandable for one person, and it's easy to understand the whole thing, the whole code that's there. What we need for those things to be efficient with this new architecture. So first, we really needed to be strong on automation. Basically, if we had one monolith and now split it into many small pieces, we no longer are able to do those things manually, or actually to have any manual steps required, because it would be like 70 times more bigger amount of work. Also, automation gives us consistency. So we really need to be sure that all different pieces are consistent with configuration, all the parameters, all the resources that they get. And we need to enable self-service for our developers and all the team working with this system. So basically, it shouldn't be no longer like filling a ticket to do some change, but just any engineer to be able to do the change themselves. We approach automation with Puppet, our tool of choice for automating stuff. We've put all of this code in version control to be able to use same processes as our developers do. And we've got a rule that actually all of the configs of any server, any application should be controlled only by Puppet, so we don't allow any changes to be done manually. As a result, we've got deployments that are fully automated, so actually no human intervention is required during deploying a new version, and we were able to significantly shorten the time needed for deployment. So it used to be 2 days of work, and now it's just half an hour from push the button to all the code deployed in production and already used by our users. And actually it's all done by automation. So it don't require human to do this. Another area that is very important for us is monitoring. So moving much faster and having so many small moving parts, we really need this feedback loop to be fast. So when we do any kind of change, we should be able to see results of it within seconds. So no longer waiting 10 minutes for observing effects is okay. It should be really rapidly visible. For this, just to tell you about few areas that we think are important for us here. So first we focus on the most detailed kind of data, so the logs and metrics, which gives us opportunity for example, tracing the applications down to a single request even, or the metrics that we use to really measure everything that moves in the system. So each call between services, each call to the data store or any other thing that application does should be measured and then visualized on dashboards. All of the monitoring, it is also fully automated the same way as we automate application. So it's also important for us to have all this set up in version control, to have not only the metrics that we take, the checks and stuff like that, but also all the dashboards controlled, so we are able to be sure about how does this evolve. And what we focus on in monitoring, it's mainly the user experience. So it's no longer so important to think about resources usage or state of different services, but we find the most important data that we have about how our users use the service, how many requests we get, how many errors are there, what is the delay of serving requests. And one more thing on monitoring front, what should we alert on? As there is a team responsible for responding for those alerts. If we alert on something, it could possibly wake someone up at night and then they need to fix the thing. So we have this rule that we should alert only when we can say that the user experience is bad or when we can predict that it will be bad soon. Now, just also a few words on the more on the culture side. So how we needed to change. How do we work? First is sharing here of all the information, all the learnings, everything that we know about the system. So if the system is composed from such many components and it changes all the time, we need to have really fast information flow between different teams, everyone working on that. How we do this? So we really try hard to use the same tools for each and every team, like having automation or monitoring tools. It's the same one for developers, for QA, even for business. They should also look at the very same dashboards, visualizing what's happening in the system. And we also share knowledge and learnings. This learning, so just to give you an example, for example, if any kind of failure happens, then we've got a rule that we always, after a failure on production, meet for a post-incident review or a post-mortem, as you call it. And the reason for this learning session is actually to be able to discuss how the system behaves, how does it work, how it fails, to understand better what are the failure scenarios, and maybe to come up with some ideas how can we improve. Another area on the culture side is collaboration. So all our teams really need now to collaborate very closely. How we do this is just one example here. While making this transition from one approach, the monolith, to the other, we have actually moved our desks to sit both teams, operations and developers, in the same office area. And then we've seen amazing things that started to happen. Basically, we started to talk to each other every day. And no longer it happened that someone needed to wait for hours or days even for the other team to react, to respond for some request. Another one here is our attitude towards failure. So as it did with the monolith, now with microservices, failures still do happen. But now we actually have this idea that we should not try to prevent any kind of failure or to predict everything that possibly could happen, but rather that it's better to move fast to deliver a change and then be able to observe, to see results very fast, and if something breaks, to be able to respond quickly, either by reverting the change or fixing it very fast. By doing this, we are also able to learn way faster, because we learn by observing how those things work. And now I'd like to give you just a very short, simple view of how this system is architectured. First is a very simple example of microservices to give you just a rough idea. So we've got one application here, which is user notification app, which purpose is to basically send messages to our users. But to do its job, it doesn't have all the functionality within itself. It needs, for example, to have information about user, basically to have the IDs of notification channels that are used. So there is another application, config repo, that owns a database and could deliver this data. Then, after obtaining this data, our app asks another application, which we call notification app, for actually sending out the message. And this notification app, it has the functionality of talking with different notification providers like Google, Apple, and others. And here, it's just a rough idea about the architecture. Basically, it's very simplified, and it's because we realize that we are no longer able to draw the whole picture of how all those components are interconnected and how they work. I will only say a few words about few rules that we have here. First of them is what means of communication are allowed between components. So if one application wants to talk to another, they could do this either by HTTP REST requests, or another possibility is to use message queue. So we've got RabbitMQ, and they could publish a message and another subscribes to it. One more architecture rule that I would like to talk about is data storages. So we used to have with a monolith a single data store for keeping everything that we need to store, and now we've got specialized data stores. So for keeping state that doesn't need to be persistent, we've got Redis cache. For keeping events that there is a huge amount of them coming to the system all the time, we use Elasticsearch, which is very performant in this usage. And then for keeping anything like configuration that we need to store and make sure it's consistent, we use the relational database for it. So we've got many of those databases, and we've got the rule that each database has to be owned by just one application, just one microservice. So then if any other app needs to get the same data, they actually need to ask the owner application for getting data from database. And I would also like to tell shortly how we approach migration. So to migrate from monolith to microservices, if you look for what people advise how to approach it, most often they say do it one byte at a time. So cut small pieces of your monolith and put it in microservices and let it serve your production traffic. So we've started with this approach and did it for a couple of months, but down the road we realized that we are actually not able to complete the task this way. Basically, our monolith was so tightly coupled within, and all the data in the single data store also heavily coupled, that we thought it wouldn't work this way. So we decided to change plan and to have another approach. Basically, we've built the new version of our platform next to the existing one. So there was our monolith and the microservice platform just next to this one. And while doing this, all of our users were still served by the monolith, but all the automated testing that we had ran on both platforms. Then we've also run load tests to simulate the high volume of traffic that we have on the new platform. And when after some another few months we are already quite confident that functionality is the same on both sides, we then started to move our users one by one to this new microservice platform. So basically we started with beta testers, observed how it worked for them, and then moved the rest one by one. And actually, at the beginning, we thought it's a high-risk approach to migrating things, but actually it went surprisingly well for us without any big disaster down the way while doing this. So how we've benefited from using this second generation of microservices. First big benefit is way faster iteration time. So now we iterate every day. The platform changes each and every day for our users, and compared to 1 month, it's a big change. How frequently are we able to release software? It used to be once per month. Now it's something like 10 times per day. Our deployments are fully automated, so it's a lot less of work for operations team. We can focus in this team on automating stuff and no longer on doing something manually. And another big win for us is on the failures. Basically, first improvement here is that with the old system, if it failed, it very often took us something like 4 hours or even much more to fix the problem. It was such complicated inside this single app that we really struggled to fix if anything bad happened. With the new approach, it's practically always take us no longer than half an hour to fix a problem. And also there is one other big difference here. With microservices, if some failure happens, it's just a very small part of functionality. Basically, as you imagine with those architecture pictures, it could happen that just only the notification part doesn't work and all the other functionality is still okay. So actually now, when we do have failures, quite often it is that our users don't even notice that something's wrong. What we've learned while doing this change. First lesson was that to do microservices, it really requires us to implement, to use most of the well-known DevOps patterns. So all the things that I've talked about in the last 20 minutes, it was just required. We were no longer able to work the old way of working with microservices. Another one, we needed to invest heavily in observability, in monitoring, basically to be able to see instantly what's going on and to see this in very detail. We also need to constantly look for a right balance between velocity of delivering changes and reliability of our system. Basically, there's this rule that the faster we try to run, the more probable it is that some accident may happen. So we work constantly on improving both sides here. One limiting factor that we found was actually our ability to learn fast. So because of those small pieces moving very fast, evolving very fast, we need to invest a lot of time on learning how those things work. And our ability to adapt is very important. We now see that we are no longer able to plan in very detail what we want to do, but rather we need to see the general direction, what effect do we want, but then while executing, we are adapting all the time to what we find, what we've learned when implementing some change, some new functionality. What issues did we see? What was problematic? First is about velocity again, and it's the result of this scale of architecture. If we have so many pieces, like 70 microservices, imagine a security issue there, and then if you need to patch all of them and deploy all 70 apps to production, if it's half an hour for deploying one and observing results, multiplied by 70, it's still quite a lot of time. So we think we need this time to be even shorter by another order of magnitude. Then complexity of this thing, it's something hard to grasp. And actually what's even harder is when we find that this complexity is reflected in our automation. So we have a lot of custom written code in Puppet, which automates all the behavior of applications, of deployments and so on. And we now realize that it is very hard to understand for someone who hasn't written it, and also it's difficult to modify, to evolve it further. Another lesson is the model of working with infrastructure. So our current model is very host-centric. So we concentrate on putting the right configuration to each node on the environment, to configuring applications on them. Also things like monitoring, they are also set up on host-based. And it seems to us that it's not the optimal approach, because our developers, they shouldn't really care about how the node is configured, but what they care about is to have a given application in a given version deployed to production, to have it run in such many instances that's required to handle a traffic that we have, and provide proper configuration for this app. And one more thing, could we really expect the only one tool to fix all our needs, to cover all those? So we rely on Puppet, which is a great tool for its purpose. So for configuring a host, operating system, services on those, but probably for operating a cluster of machines and applications of them, there should be better tools for that. So, as we already see these issues there, we are also already thinking about how can we evolve further, where to move from where we are. So the idea here is to go for a cloud-native platform that I would try to introduce shortly to you. So first reason why we try to go this direction is again about speed. So how to increase again to move even faster from idea that we have to putting it out to our customers. we should be able to scale very dynamically our platform, so react to changes in demand from our users. And while doing this, we should also have very good reliability, so to always be sure about that it all runs okay. And one more thing that it should improve, it should be way better efficiency of resources usage. So if we are able to change dynamically how much resources do we consume in the cloud, we should be able to cut our infrastructure bills. And again, we think that focusing just on VMs and those and configuration of those, it's not the best abstraction to work with apps. So we should rather think about the whole cluster as a single machine and have a way to actually define what state of the cluster and application running on this should be. Our approach to this, it started something like 2 years ago with just some experiments and discovery of different kinds of tools that are available. So as we were already using Docker for containerization of all our apps, we've tried to find what tools can automate those for us. So we've tried 3 of those. There was Docker Swarm, Kubernetes, and Nomad. And our results back then were like Docker Swarm didn't seem to be a complete solution for automating apps running on the environment and serving traffic. Kubernetes was a very complex thing, very hard to understand, and also it was very difficult to deploy back then. And then there was HashiCorp Nomad, which we found quite good on the completeness of what it covered, and also not so difficult to deploy, like quite straightforward. So after this discovery of different tools, we decided to continue with some experiments. We decided to go further with Docker Swarm, but just as a platform for our Jenkins tests. So what we've done was we moved all of our Jenkins slaves from virtual machines to Docker containers running in Swarm cluster. And this change was also a big win for us, because now we've got all the environment for tests consistent, the dynamic resources given dynamically to those tests, and it improved this area a lot. Another thing that we found that might work well was Nomad as an orchestrator for applications, but actually back then it wasn't really the highest priority for our business, as we've just finished migration to microservices and had different business requirements at the moment. So we weren't able back then to move further with this. But there were some important lessons that we've learned then. First of them is that usage of orchestrator is really a big change for how we do things. It would change everything about how we approach automation, how we configure our apps, how we set interconnections between them, how do we do monitoring. For example, if those services would be very fast coming up and going away, then our tools that we use that are host-centric, probably they would not work very well. So we would need to change those areas. Also, we now see that it is really a lot of learning required to approach the environment this way. So to learn all the new tools, all of the new methods of how we operate stuff. And how do we try to approach this learning? So as we are in the process right now, what do we have? We found this Cloud Native trail map from Cloud Native Computing Foundation, which is just a very nice guide into how to go through all the different ideas, technologies, and so on. So they basically say that you start with containerization of your applications, then you focus on continuous integration, continuous delivery. You should probably at this point already have it split to microservices, and then you employ orchestrator to manage your services. And those three are like the mandatory steps to go into cloud native methods. And there is another good summary of what goes into cloud native methods of working. So there is this book from Anna Curie who described some of the best practices and lessons they've learned with working with different customers. And they list just 5 points of what makes a cloud native platform. So it is a platform based on infrastructure as a service. Then you need a microservices architecture to work with those small pieces of software. You need to put those applications in container to be sure about all the dependencies, everything that it's required to run the app. Then to fully automate everything that happens. And the last one is to orchestrate it with some really software-based solution for automating the whole environment. So for us, it's like with our current platform, we are already done with those all those first 4 points here. It's all in containers and automated, but the orchestrator is the last big change that we still need to do. So, just to give you a brief summary of what I've talked about today, there were 3 parts. So first was about monoliths, that they really makes you slow. At least our experience was that we couldn't run any faster with monolithic architecture. Then the microservices, that we've observed great benefits from using those, but also there were very big challenges. So we needed to invest a lot of work to this migration and to change the architecture. And the third one is cloud native, and that we think that to be able to fully benefit from microservices, we do really need those methods, this approach for working with a cluster and to automation. So that's all that I have for you today. I'm Tomasz Tarczyński, and thank you very much for listening.